For millennia, humans gazed at the stars, pondering the nature of the cosmos. The night sky, with its twinkling stars and mysterious patterns, has always been a source of wonder and curiosity. What were those celestial fires that illuminated the night sky? Were they gods, spirits, or something else entirely? These questions have echoed through the ages. We sought answers in mythology and philosophy, crafting stories and theories to explain the heavens. Yet, despite our best efforts, the true nature of the universe remained elusive, shrouded in mystery and speculation. Then, science began to illuminate the darkness. With the advent of the scientific method, we started to peel back the layers of the unknown, seeking empirical evidence and logical explanations. At the dawn of the 20th century, a revolution was brewing in the world of physics. The old paradigms were being challenged and new ideas were emerging, promising to transform our understanding of the universe. Scientists were peering deep into the heart of matter, probing the atom, the fundamental building block of everything we see and touch. They were driven by a desire to uncover the secrets of the microscopic world. The prevailing theory at the time imagined the atom as a miniature solar system, with electrons orbiting a central nucleus like planets around a star. This model, while elegant, was about to face a significant challenge. This model, while intuitive, was about to be shattered. New experimental evidence was on the horizon, ready to upend our understanding of atomic structure. In 1911, Ernest Rutherford, a New Zealand-born physicist, conducted his now famous gold foil experiment. This groundbreaking experiment would change the course of science forever. He bombarded a thin sheet of gold foil with alpha particles, expecting most of them to pass straight through. This was based on the assumption that the atom was mostly empty space. To his astonishment, some particles were deflected at sharp angles, a result that could only be explained if the atom's mass was concentrated in a tiny, dense nucleus at its center. This was a revelation that defied the existing models. Rutherford's experiment was a turning point. It not only challenged the prevailing atomic model, but also opened up new avenues of research and inquiry. It revealed that the atom, far from being a solid, indivisible entity, was mostly empty space, with a tiny, positively charged nucleus at its core. This discovery fundamentally altered our perception of matter. This discovery laid the foundation for our modern understanding of atomic structure. It set the stage for future breakthroughs in quantum mechanics and particle physics, fields that continue to expand our knowledge of the universe. It also paved the way for a new era in medicine, one in which the invisible world of atoms would be harnessed to diagnose and treat disease. From X-rays to MRI scans, our ability to peer inside the human body owes much to our understanding of atomic structure. As we continue to explore the universe within, we uncover more about the fundamental nature of reality. Each discovery brings us closer to understanding the intricate tapestry of existence, woven from the threads of atoms and particles. The journey from the stars to the atom is a testament to human curiosity and ingenuity. It reminds us that the universe, both vast and minute, is a realm of endless wonder and discovery. Rutherford's groundbreaking discovery of the atomic nucleus in 1911 was just the beginning of our journey into the heart of matter. His work laid the foundation for a deeper understanding of atomic structure. Scientists soon realized that the nucleus itself was not a simple, indivisible entity. Instead, it was a complex structure composed of even smaller particles, which they would come to identify as protons and neutrons. These subatomic particles, protons and neutrons, are fundamental to the atom's identity and its properties. Protons carry a positive charge, while neutrons are neutral, and together they form the core of the atom. The number of protons in the nucleus, known as the atomic number, is what determines which element an atom belongs to. This atomic number is a unique identifier for each element on the periodic table. For instance, all carbon atoms have 6 protons, while all oxygen atoms have 8. This distinction is crucial in defining the chemical behavior and characteristics of each element. However, atoms of the same element can differ in their number of neutrons. These variations do not change the element itself, but do alter its atomic mass. These variants, known as isotopes, share the same atomic number but have different atomic masses due to the differing number of neutrons in their nuclei. For example, carbon-12, the most common isotope of carbon, has 6 protons and 6 neutrons, giving it an atomic mass of 12. This isotope is stable and does not undergo radioactive decay. In contrast, carbon-14, a radioactive isotope, also has 6 protons but possesses 8 neutrons, resulting in an atomic mass of 14. This isotope is unstable and is used in radiocarbon dating to determine the age of archaeological finds. This difference in neutron number is crucial because it affects the stability of the isotope. The balance between protons and neutrons determines whether an isotope will be stable or radioactive. While some isotopes are stable and remain unchanged over time, others, like carbon-14, are unstable and undergo radioactive decay. This process is a natural phenomenon where the nucleus emits particles or energy. This means they spontaneously emit particles or energy from their nuclei, transforming into a different element in the process. This transformation can release significant amounts of energy. This phenomenon, known as radioactivity, would prove to be a double-edged sword. It is both a source of potential harm due to its radiation and a powerful tool for good used in medical treatments, energy production, and scientific research. To understand the power of radioisotopes, we must delve deeper into the concept of isotopes themselves. Isotopes are variants of a particular chemical element that have the same number of protons but different numbers of neutrons. This difference in neutron number gives each isotope a unique nuclear mass. Imagine a group of musicians, each playing the same type of instrument, say a violin. In an orchestra, the violin section works together to create a harmonious sound, much like how isotopes of an element contribute to its overall properties. Each violin produces a characteristic sound, a unique timbre that distinguishes it from other instruments. This is akin to how each isotope has its own unique properties, despite being part of the same element. Now imagine that some violins are slightly heavier or lighter than others due to variations in their construction. These differences in weight can be compared to the differences in neutron numbers among isotopes. These subtle differences in mass wouldn't fundamentally change the sound of the violin, but they would introduce subtle variations in tone and resonance. Similarly, the differences in neutron numbers among isotopes don't change the element's chemical properties, but do affect its nuclear properties. Isotopes are like those violins. They are variations on a theme, atoms of the same element with the same chemical properties, but with slight differences in their nuclear mass. This variation can lead to different physical properties, such as stability and radioactivity. They are variations on a theme, atoms of the same element with the same chemical properties, but with slight differences in their nuclear mass. These differences can have significant implications in various fields, from medicine to energy production. And just as those subtle variations in a violin's mass can affect its sound, the differences in neutron number among isotopes can have profound implications for their stability and behavior. Some isotopes are stable, while others are unstable and prone to radioactive decay. Some isotopes are like perfectly balanced violins, their nuclei humming with stability. These stable isotopes do not change over time and are found naturally in the environment. These are the stable isotopes, the ones we encounter in our everyday lives. They are used in various applications, from carbon dating to medical diagnostics, due to their predictable behavior. But other isotopes are like violins with an extra weight on one side, their nuclei teetering on the edge of instability. These unstable isotopes are radioactive and can decay over time, releasing energy in the process. These are the radioactive isotopes, and their tendency to decay, to shed that excess nuclear energy, is what makes them both fascinating and useful. Radioactive isotopes have applications in medicine, such as in cancer treatment, and in energy production, where they are used as fuel in nuclear reactors. Their unique properties make them invaluable tools in scientific research and practical applications. Section 4, the Curie legacy, a family affair.
The discovery of radioactivity and the exploration of isotopes would not have been possible without the pioneering work of my husband Pierre and myself. This scientific duo dedicated their lives to unraveling the mysteries of radiation, conducting groundbreaking research on elements like uranium and thorium.
Their discoveries laid the groundwork for our understanding of radioactivity and its applications.
Born Maria Skłodowska in Poland, I faced immense challenges in my pursuit of science.
In an era when women in science were rare, she persevered, becoming the first woman to win a Nobel Prize and the only person to win Nobel Prizes in 2 different scientific fields, physics and chemistry.
Her legacy would inspire generations of scientists, including her own daughter, Irene Joliot-Curie.
Irene, following in her parents' footsteps, made significant contributions to the field of nuclear physics.
Alongside her husband, Frédéric Joliot-Curie, she discovered artificial radioactivity, a groundbreaking achievement that would earn them the Nobel Prize in Chemistry in 1935.
This discovery, building upon the Curie's earlier work, opened up a new realm of possibilities for medicine and technology. Section 5, the dawn of artificial radioisotopes.
The Joliot-Curie's discovery of artificial radioactivity was a pivotal moment in scientific history.
We demonstrated that stable atoms could be transformed into radioactive isotopes by bombarding them with certain types of particles.
This groundbreaking finding shattered the long-held belief that radioactivity was a phenomenon limited to naturally occurring elements like uranium and radium.
Imagine a sculptor skillfully shaping a block of clay into a work of art.
The Joliot-Curies, through their experiments, revealed that scientists could, in a sense, sculpt atoms, transforming stable nuclei into radioactive ones.
This newfound ability to create artificial radioisotopes opened up vast possibilities for medical research and diagnostics.
Prior to their discovery, doctors relied solely on naturally occurring radioisotopes, which were often expensive, difficult to obtain, and limited in their applications.
Artificial radioisotopes, on the other hand, could be produced in laboratories, tailoring their properties to specific medical needs.
This breakthrough paved the way for a new era in medicine, one where radioactive isotopes would be used to diagnose, image, and treat a wide range of diseases.